Hello, my name is Martin, and this is the first in a series of videos about BabyCube, a 3D printer I've designed and built. BabyCube is a small linear rails based CoreXY printer. Its dimensions are approximately 22 by 20 by 22 centimeters. That's about 8.5 by 8 by 8.5 inches. And it weighs about 4 kilos, just under 9 pounds. Let's switch it on. You'll notice BabyCube is silent at startup. That's because of the way the fans are managed. The main board is thermally connected to the aluminium base plate, which serves as a heat sink, so no fans are required for the stepper drivers. The hot end cooling fan is thermally controlled and does not come on until the hot end reaches 50 degrees. And the part cooling fan is controlled by the G code and so won't come on until printing begins. Finally, a laptop power supply is used, so that doesn't require a fan. The end result is the printer is entirely silent until you start printing. Let's disconnect it and have a look at it. The spool holder is detachable and can be placed inside the printer for storage. The main board is a Big Tree Tech E3 Mini and it's attached to a TFT35 display. I'm running Marlin on this, but there's room for Raspberry Pi here, so you can run Clipper if you want. There's also room for a board that supports RepRap firmware, for example a BTT E3 Turbo or a BTT SKR 1.4. The on-off switch is on the front panel and can be used as an emergency stop. The belts are accessible at the front, allowing you to check tension or use a tension measuring device. The hot end is a genuine E3D V6 with 30mm fans for both the hot end and part cooling. It runs on MGN 9mm rails, one for the X-axis and two for the Y-axis. From the side you can see the XY stepper motors. These are NEMA 14 stepper motors. There's a window here which serves three purposes. Firstly, it allows the X and Y motors to be offset by an additional 1mm to give 2mm of additional internal space. Secondly, it allows for cooling of the stepper motor. And thirdly, it allows you to test the stepper motor to see if it's running hot. There's cutouts on the frame for zip ties to manage the wires to the stepper motor. Homing is sensorless, so there's no wires for end stops. The PSU is a 19-volt laptop power supply and it's connected via XT60 connectors. The reason I've used those is it allows you to remove the power supply and replace it with a LiPo battery if you wish. That allows you to run entirely free of mains power. You can see I've used finger joints to join the side, back and top panels. There's three reasons for that. One, it gives a little bit of an additional rigidity to the frame. Secondly, I just like the look of it. Thirdly, I'm designing a variant with a carbon fiber frame and this provides proof of concept. The Z-axis is driven by a NEMA 17 stepper motor with an integrated lead screw. The Z carriage runs on 12mm linear rods. The reason I've chosen them is because if I used 8 or 10mm linear rods, the brackets holding them would not be long enough to allow the linear rods to line up with the lead screw without using spacers. And it turns out that 12mm linear rods aren't that much more expensive anyway. Sensorless homing is also used on the Z-axis. The home position is at the bottom though, so there's no danger of the hot end crashing into the print bed during homing. There are cutouts for zip ties for cable management The screws are all countersunk, which means the back face is entirely flush, which means if you keep it on your desk, you can push it right up against the wall to get it out of your way. On the right side we have the connection for the power supply, and we can see how the wiring to the hot end is managed. The wiring runs down the back here, underneath the power supply, and is connected to the main board at the front. As I mentioned before, there's room for a Raspberry Pi Zero here if you so desire. There's a dual geared extruder connected to the hot end via a Bowden tube. Here's a little demonstration to show the rigidity of the frame. I'll take a 5 kilo dumbbell and place it on the print bed. As you can see, the deflection is 0.3 of a degree. That's it for now.